Welcome to the Data Genius podcast. So glad you were joining us today.
Yeah, it's going to be a really fun one.
It is, because right now, literally as we speak, millions of dollars are being poured into enterprise artificial intelligence projects.
Oh, absolutely. Billions even.
Right. Companies are just racing to deploy these digital workers. They assume these systems will instantly automate their most complex workflows.
Which is a huge assumption.
Exactly. And there's this massive discrepancy between the boardroom expectations and the actual engineering reality.
Yeah, the gap is wild.
It's huge. According to recent industry research from MIT and a few other institutions, nearly 95% of enterprise generative AI pilots fail to deliver any measurable return on investment.
I mean, 95%, that is just a staggering number.
It really is.
Especially when you consider the raw capability of the underlying models we have access to today. The compute is there, the reasoning capability is there.
And yet they completely fail when put into production.
Yeah, they do.
So, today's mission is to decode the actual mechanics of agentic AI. We are unpacking exactly why these pilots crash and burn.
Which, spoiler alert, almost always comes down to weak instructions.
Right, and just a fundamental misunderstanding of how autonomous systems actually operate in the wild.
For sure. It's a completely different paradigm.
So by the end of this deep dive, you are going to understand the exact frameworks required to build these systems.
We're going to expose all the hidden traps, too.
Yeah, things like structured output failures and context rot.
Oh, context rot is a huge one. We will definitely get into that.
And we'll detail the rigorous evaluation methods you need to turn an unpredictable language model into a highly reliable digital teammate.
What's really fascinating here is that fixing this 95% failure rate isn't just about tweaking a few words in a prompt.
Right, it's not just prompt engineering.
Exactly. It requires a complete paradigm shift in how we approach human-computer interaction.
How?
Well, for the last few decades, and especially in the last few years with standard language models, we have been prompting for conversation.
Like chatting with a bot.
Right. But now, we need to transition to prompting for agency.
Okay, let's unpack this immediately because I think this is where the confusion takes root for a lot of people.
It definitely is.
We really have to draw a hard line between a chatbot and an agent. On the surface, I mean, they look identical.
Totally. You have a text box, you type a request, and something happens.
But under the hood, it's totally different. A chatbot generates text while an agent executes work.
That's the core distinction right there.
There is a software infrastructure company called Speakeasy, and they framed this using a programming parallel that I think perfectly captures the architectural difference.
Oh, I love this analogy.
Yeah. They describe chatbots as for loops and agents as while loops.
Right. So if we think about a standard for loop in traditional software engineering, its defining characteristic is predictability.
It does exactly what you tell it to do.
Exactly. It runs a predetermined number of iterations based on a fixed set of inputs.
So when you interact with a chatbot, it's just a loop.
Yeah. You are initiating a single bounded transaction. You provide a prompt. The model processes those specific tokens. It generates a text response, and then it completely stops.
It just goes dormant.
Exactly. It goes to sleep. It has absolutely no awareness of whether that text actually solved your problem. Its only job was to generate it.
It's like a ping pong match. You hit the ball over the net, the machine hits it back, and the volley is over.
That's a great way to put it.
It's fast, it's impressive, but it is entirely contained to the table.
Right.
An agent, however, is a completely different beast.
Because an agent operates on the logic of a while loop.
Which means it keeps going.
Yes. A while loop in programming runs continuously until a specific condition is met.
So how does that look for an AI?
Well, an agent observes its environment, analyzes the state of that environment against its assigned goal, makes a decision on what tool to use, and takes an action.
And then it stops.
No, and this is crucial. It evaluates the result of that action. If the goal is not met, the loop starts over.
Oh, wow.
It replans and iterates continuously while the objective remains incomplete.
Okay, let's look at a real-world scenario to ground this. Let's say I want to organize a meeting.
Sure.
A regular prompt to a chatbot is just, draft an email to the marketing team proposing a meeting for next Tuesday.
And it does a great job at that.
It does. The chatbot writes a great draft, outputs the text, and goes to sleep. But I still have to copy it, open my email client, paste it, find the email addresses, and actually hit send.
You're still doing the actual work.
Exactly. But an agentic prompt acts as an operating manual. I'm telling the system, find a time next Tuesday when the marketing leads are free, book the conference room, and send calendar invites.
Which means the system has to operate autonomously across multiple steps.
Right.
It has to check a calendar API, realize someone's on PTO, replan its approach, check Wednesday instead, interface with the room booking software.
Handle a potential permission error if the room is locked.
Exactly. And then finally dispatch the invites.
Giving instructions for that kind of workflow is literally like giving someone your credit card, handing them the keys to your car, and sending them to the grocery store.
It's a huge delegation of authority.
Yeah, you aren't just giving them a list of ingredients. You have to establish completely different rules of engagement.
Like what?
Like, what is the maximum budget? What happens if the store is out of organic milk? Do they substitute it, go to another store, or just skip it? What routes are they allowed to drive?
And this brings us to why generic, copy-pasted prompts completely break down when deployed in an enterprise environment.
Because every company is different.
According to the research team at EME AI, generic instructions fail because every single company operates on a totally unique, idiosyncratic technology stack.
And unique business rules, too.
Exactly. You can't just take an agent that flawlessly handled customer service at company A, export its system prompt, drop it into company B, and expect it to just work.
Never. Because company A might use Salesforce for CRM, Slack for internal communication, and have this rigid two-step managerial approval process for any refund.
Right.
But company B might use HubSpot, Microsoft Teams, and only require approval for refunds over $50.
So if you deploy an agent into company B with a generic prompt like, resolve customer billing issues, it completely lacks the organizational context to navigate that specific environment.
It doesn't know the layout of the grocery store.
It doesn't. And when an agent lacks context but still has a directive to complete a task, it attempts to fill in the blanks using generalized knowledge from its training data.
Oh, so just guesses.
Yeah, and this is exactly where we see workflow hallucinations. The agent will attempt to make an API call to Salesforce because statistically, that's what it expects a corporate company to use.
And when that fails,
It might try to bypass an HR policy it doesn't know exists, or it might confidently tell the customer a refund has been issued when it never actually triggered the internal HubSpot workflow.
because it just hallucinated the whole process.
Yes, the prompt has to be mapped to the exact digital terrain it is navigating.
Which raises an immediate practical challenge. If agents require this incredibly deep level of environmental instruction to operate, how do we write those instructions without micromanaging the AI to death?
It's a tough balance.
Because if I have to spend 3 hours writing a 500-page manual explaining every single button click for a task, the automation is pointless. I might as well just do the task myself.
Anthropic tackles this exact dilemma with a concept they call finding the right altitude.
The right altitude, I like that.
Yeah, it is the engineering practice of finding the Goldilocks zone for your system instructions.
Not too high, not too low.
Exactly. The altitude of your prompt needs to be low enough to meaningfully constrain the agent's behavior and keep it safe, but high enough to remain flexible when it inevitably encounters the messy reality of live enterprise data.
And we see two distinct failure modes when developers miss this altitude.
Oh, constantly.
Let's look at failure mode 1, which is the overspecified prompt. This happens when engineers treat the language model like traditional deterministic code.
Like they're writing Python or something.
Yeah, they write these massive, brittle prompts that read like endless Eiffel's flowcharts. If the user asks about billing, query database A. If database A returns an error, ping the manager. If the manager doesn't reply in 5 minutes.
And the problem there is the moment the user asks something that deviates even 1 degree from that hard-coded flowchart.
Like if they ask about billing and a technical support issue in the exact same sentence.
Right. The entire script just shatters. The agent doesn't know how to route that dual intent because the instructions were way too rigid.
Then we have failure mode 2, which is the underspecified prompt.
And this is usually written by someone who is a bit too used to highly capable consumer chatbots.
Right, they just type, help the user.
Exactly. They give the enterprise agent a vague directive like, you're a helpful assistant. Help the user resolve their issue. They just assume the AI inherently shares their understanding of the company's unwritten rules.
But it doesn't share that context at all.
No, it doesn't. So when you provide an underspecified prompt, the agent either becomes paralyzed and constantly asks the user for clarification on every tiny step,
Which is super annoying.
or worse, it goes completely rogue. It starts making massive assumptions, pulling in tools it shouldn't use, and hallucinating solutions because the altitude was way too high.
This distinction really crystallizes when we look at outcome-oriented prompts versus procedural prompts.
This is a vital difference.
Let's say I need an agent to process a weekly sales report. A procedural prompt dictates the exact mechanics. It says, open the sales CSV file, find the column labeled revenue, sum the values by region, create a new Word document, paste the table, and save it to the shared drive.
Very step-by-step. But an outcome-oriented prompt, on the other hand, defines the final state of the world you want to achieve.
What does that look like?
It looks like this. Analyze the weekly sales CSV and produce a summary document detailing total revenue by region while explicitly highlighting any data anomalies or missing entries.
The engineering blog at Confluent uses a fantastic analogy about instructing a chef to explain this difference.
It is brilliant in its simplicity. Imagine walking into a high-end restaurant kitchen.
Okay, I'm there.
If you tell the master chef, make something delicious, that is failure mode 2. It is completely underspecified.
Because you might get a bowl of soup or you might get a chocolate cake.
Both delicious, but neither is what you wanted for a main course.
Right.
But if you walk into that same kitchen and tell the chef exactly how to grip the knife, what angle to hold the blade, how many millimeters thick to dice the onions, and exactly what temperature to set the burner.
That is failure mode 1.
Yes.
Yeah.
You are overspecifying. You are constraining a highly capable expert system.
So if the onions delivered that day are slightly larger than usual, your rigid instructions might result in them being undercooked.
Exactly. So
Yeah.
finding the right altitude is walking into the kitchen and saying, make an herb-roasted chicken with root vegetables.
Ah, I see.
You define the specific outcome, but you allow the expert system to utilize its reasoning to handle the actual execution.
But wait, I have to challenge that approach, especially in the context of enterprise deployment.
Okay, go for it.
If I am building a system that interacts with secure financial data or sensitive patient records, isn't it inherently safer to give the AI that rigid, step-by-step procedural checklist?
It feels that way, yeah.
Right. I don't want it improvising with a database. I want to control exactly what it touches and in what exact order.
It intuitively feels safer to a traditional software engineer, for sure. But in the context of autonomous agents, procedural rigidity actually creates a highly fragile system.
How so?
Let's trace the execution of that procedural CSV prompt we discussed earlier.
Yeah.
Step 1 was find the column labeled revenue. What happens on a Tuesday morning when the finance team updates their software and the new CSV export renames that column to rev_Q3_final?
Oh, a procedurally prompted agent will just crash.
Yeah.
It will hit that step, search for the exact string revenue, fail to find it, and just throw an error loop.
Precisely. Because it was programmed to follow a syntax, not to understand semantics.
But the outcome-oriented agent would handle it.
Yes, because it's prompted at the right altitude.
Right.
It understands the underlying goal is to calculate financial totals by region.
Right.
So it'll look at the headers, use its semantic reasoning to deduce that rev_Q3_final contains the financial data it requires, adapt its extraction method, and successfully complete the task without human intervention.
Wow. And that adaptability is the entire value proposition of generative AI.
Exactly.
If you want a system that crashes every time a column header changes, you don't need a massive neural network. You just need a 20-line Python script.
You could just use Excel macros at that point.
Exactly. So how do we systematically structure an outcome-oriented prompt that balances that freedom with safety? EMA AI laid out the core building blocks of an agentic prompt, and it serves as a phenomenal architecture checklist.
It really does. They identify 8 mandatory components.
Let's go through them.
The first component is the goal or outcome. As we discussed, this must state the desired final state, not the sequence of tasks.
Right. The roasted chicken, not the knife angle.
Yeah, exactly. The second is role and authority. The system needs to know who it is representing and, more importantly, what actions are strictly outside its jurisdiction.
Third is context. This is where you inject the environment variables.
Things like user attributes, right?
Yeah, what are the user attributes? What happened in past interactions? What are the SLA timelines for this specific task?
That makes sense.
Fourth is tools and data access. This must be a highly explicit inventory of the APIs and databases the agent can tap into.
And you have to clarify the permission state, too.
Right. Does the agent have read-only access to the CRM, or does it have full write access to actually change customer records?
Fifth is process rules. And this differs from a procedural checklist.
How so?
Process rules establish the broad methodology, for example, dictating a sequence of Diagnose first, fetch context second, act third, log the result fourth.
Ah, so it enforces a logical flow without micromanaging the individual clicks within those phases.
You got it.
Number 6 is output format. When the job is done, how should the agent report back? Are we expecting a machine-readable JSON payload, a brief Slack message to a manager, a detailed audit note in Jira?
All the very different formats.
Very. Number 7 is guardrails. What are the predefined escalation paths? If the agent encounters a task outside its authority, who does it ping?
And what actions are categorically off limits under any circumstance?
Exactly. And finally, the 8th component is the self-check mechanism.
This one is huge.
It is. This is a behavioral instruction telling the agent to pause, verify its own assumptions, and run a compliance check against its guardrails immediately before executing any state-changing action.
To ground this in reality, EMA AI provided a blueprint for an L1 support agent using these exact blocks.
And the goal in the prompt is not defined as answer customer support ticket.
No, that is way too vague.
The goal is explicitly defined as bring average ticket resolution time under 15 minutes while maintaining customer satisfaction scores at or above 4.5.
That is just a masterclass in outcome-oriented prompting.
It really is.
By anchoring the agent's behavior to tangible business metrics, you provide it with the true north.
So when it encounters a really weird, highly ambiguous customer situation that isn't covered by the FAQs,
It doesn't just guess blindly. It evaluates its potential responses against those metrics.
yeah.
It asks itself, will this action resolve the issue quickly while ensuring the customer feels supported?
Okay, so you have engineered the perfect prompt. You have set the right altitude, established the guardrails, and handed the agent a comprehensive toolkit to achieve that goal.
Job done. Right.
You'd think, but this is where teams walk right into a massive hidden minefield. There is a deep assumption that giving an agent more tools or demanding highly structured outputs to fit into existing pipelines makes the system more robust.
But the reality is the exact opposite.
It is, which brings us to the dangers of tool overload and the structured output trap.
Tool overload is a really fascinating psychological trap for engineering teams.
Why do they fall for it?
Well, when you first realize an LLM can trigger APIs, the immediate instinct is to connect it to everything.
Like give it all the keys.
Yeah, you think if I give my agent access to Jira, GitHub, Slack, Confluence, Google Drive, and the internal HR portal, it becomes omnipotent.
Right,
And-
but instead of becoming a super worker, it just becomes paralyzed.
Exactly. Because more tools create exponential ambiguity in the model's decision-making space.
Oh, I see.
If you provide an agent with a search Confluence tool and a search Google Drive tool, and those repositories contain even slightly overlapping information, the agent hesitates.
It doesn't know which one to pick.
When a user asks a question, the agent spends computational cycles trying to guess which tool is the most correct. Often it gets confused, selects the wrong tool, receives irrelevant data, and goes down a deep rabbit hole trying to recover.
So to solve this, the literature emphasizes heavily managing the negative space.
Yes, the negative space is just as important as the active instructions.
It's what you tell it not to do.
It is the explicit practice of telling the agent when not to use a tool, or defining the exact boundaries of a tool's utility.
A great example of this is when you are utilizing retrieval augmented generation, or RAG.
Right.
You might have already loaded 20 pages of specific product documentation into the agent's immediate context window. But if you also give that agent a live web search tool, you must utilize the negative space.
You have to instruct it explicitly.
You have to say, do not use the web search tool to retrieve general product specifications as they are already provided in your context.
Because if you don't define that negative space, the agent will inevitably ignore the loaded documents
Waste time, burn API budget,
and risk pulling outdated information from the live web.
which perfectly transitions us to the biggest engineering trap we need to discuss today.
Ah, yes.
The JSON trap.
This one catches everybody.
We all know that enterprise software runs on structured data. Developers love JSON. It is predictable, it parses cleanly, and it integrates flawlessly into legacy databases.
It's the standard.
But according to the engineering blog at Boundary ML, or BAM, forcing a large language model to output perfect JSON severely degrades its fundamental reasoning ability.
This is a highly technical but critical failure point.
Yeah.
To understand why this happens, we really have to look at how developers enforce this formatting. They use a technique called constrained decoding.
Let's break that down because constrained decoding sounds like a good thing.
It does.
We want to constrain the output so it doesn't just spit out a rambling paragraph when we need a data table.
It sounds ideal, but the mechanics are actually destructive. Language models generate text autoregressively.
Meaning one token at a time.
Right, they predict and output one token, which is a word, or a piece of a word, or a number at a time, based on probability.
Okay.
In a normal generation, the model considers thousands of possible next tokens. But when you apply constrained decoding to guarantee perfectly formatted JSON, you are placing a strict filter over the model's output layer.
So the system is actively monitoring the tokens as they are generated?
Exactly. The filter looks at the strict JSON schema you provided. If the schema demands that a specific field must be a Boolean-like true or false, and the model tries to output the word maybe,
The filter aggressively blocks that token.
it literally zeroes out the probability of any token that violates the structural syntax of the schema.
And this is where the wheels completely fall off. BAML provided an incredible example regarding an agent tasked with receipt parsing.
Oh, the grocery receipt example.
Yes. Imagine you have a multimodal AI agent analyzing an image of a grocery receipt. The developer wrote a JSON schema demanding that the quantity field must be an integer, meaning a whole number.
Right, no decimals.
But the agent reads the physical receipt and clearly sees a fractional quantity. Let's say it says 51.7 pounds of bulk produce.
Okay, so the model processes the image perfectly. It's highly intelligent, right? It knows the correct answer is 51.7.
Yes.
It begins to generate the JSON output, token by token, open bracket, quote, quantity, quote, colon,
Then it outputs the number 5.
then the number 1.
At this exact millisecond, the model wants to output a decimal point to write 0.7.
But the constrained decoding filter intercepts it.
The filter checks the schema, sees that the field is defined as an integer, and realizes that a decimal point violates the syntax.
So it forcefully blocks the decimal point token.
Wait, if the filter blocks the token the model knows is correct, how does the model pick the next best one? Does it just guess randomly?
It's forced to select the highest probability token from the remaining pool of syntax-approved options.
Oh, no.
The model is essentially backed into a corner. It has already written 51. It can't go back. It's blocked from writing a decimal. So it guesses the most mathematically valid next integer token it is allowed to use.
And what does it usually guess?
Very often, it will output a 0, resulting in a final parsed quantity of 510.
Wow. Here's where it gets really interesting. By forcing the AI to prioritize the structural syntax of the JSON, we are actively lobotomizing its reasoning.
We really are.
We are sacrificing the actual factual correctness of the data just to make sure the brackets match.
Yeah.
It is exactly like forcing a brilliant mathematician to fill out a highly complex bureaucratic tax form and telling them that if they put a comma in the wrong box, we will shred their entirely correct math.
It's so backwards.
We are forcing the AI to focus on putting a cover page on the TPS report before it is even allowed to do the math.
This raises an important question, though. If enterprise pipelines require structured data, how do we extract it without degrading the model's intelligence?
How do we fix it?
This brings us to a foundational design rule formulated by AI researcher Tian Pan.
Okay.
If you absolutely must use JSON output, you have to engineer the schema so that the reasoning fields appear before the conclusion fields.
Walk us through how that structural change actually impacts the model's brain.
It goes back to the autoregressive nature of the models. They read and generate left to right. They do not have a backspace key.
Right, they can't edit what they already said.
If your JSON schema forces the model to output the final answer first, for example, the schema is ordered, final decision is approve, and then reasoning is blank. The model is forced to commit to the approved token before it has processed the variables.
It hasn't had the chance to think.
It's forcing a gut reaction instead of a calculated decision.
Yeah, oh, that makes total sense.
Exactly. But if you simply flip the order of the schema to reasoning first and final decision second, you create a cognitive scratch pad for the model.
A scratch pad, I like that.
As it generates the text for the reasoning field, those generated tokens enter its context window. It literally thinks out loud, processing the logic step by step.
So by the time it reaches the final decision field at the bottom of the JSON object, it has built a logical foundation that dramatically increases the accuracy of the final output.
Precise.
And if you don't implement that scratch pad, you get what Tian Pan calls false confidence.
A worse kind of confidence.
And this is the nightmare scenario for a CIO. Because as a developer, you look at your logging console, you see this beautifully formatted, perfectly structured JSON object streaming in, and you assume the data inside it must be correct.
Because the system didn't crash.
Exactly. There are no syntax errors, but the error has simply shifted from a loud, obvious system crash to a silent, semantic hallucination.
The autonomous system is running flawlessly while making terrible, mathematically incorrect decisions in the background.
It is the most dangerous kind of failure because it goes undetected until the business impact is severe.
Absolutely.
So we have successfully navigated the immediate traps of tool selection and JSON formatting, but as we established at the very beginning, agents aren't chatbots.
Right. They don't just stop.
They don't just take one action and stop. They run continuously in those complex while loops. They might take 20, 30, or 40 actions to resolve a single workflow.
Yeah, these sessions get long.
So what happens to the AI's internal state on turn 20? This leads us to the reality of the long game, dealing with context rot and prompt drift.
The research team at Mind Studio defines context rot as the gradual, inevitable degradation of an AI agent's output quality as a session grows longer.
Why is it inevitable?
To understand why this happens, you have to visualize the context window.
Yeah.
Every single time the agent takes an action, every time an API returns a massive payload of data, every time it writes a note to itself.
All of that text gets stuffed into its working memory.
Exactly. Over a long, multi-step session, the signal-to-noise ratio absolutely plummets.
It's like trying to have a highly technical, nuanced conversation in a crowded restaurant where the background music just keeps getting louder and louder.
That is the perfect analogy.
Eventually, the model can't hear its own instructions over the noise of the accumulated data.
And this leads to a secondary, compounding issue. If an agent makes a tiny mistake or a slight hallucination early in the session, maybe on step 3 of a 30-step process, that mistake doesn't just disappear.
It gets baked into the memory.
Yes. Every future decision the agent makes is built on top of that initial error. It creates a snowball effect of hallucination.
Alongside context rot, we see a phenomenon known as prompt drift, which has been extensively documented in developer forums like Sushido and Dev community.
Drift is fascinating.
As the conversation history expands, the model pays less and less attention to the system instructions you gave it at the very beginning of the session.
Wait, why? If the instructions are in the prompt, shouldn't it follow them?
It has to do with how attention mechanisms work in transformer architectures. They suffer from a recency bias.
Ah, so they favor new information.
The models inherently weight tokens that appear closer to the end of the prompt more heavily than tokens at the beginning.
Okay, I see.
So as the session grows, those critical guardrails and negative space instructions you carefully crafted get pushed further and further back in the memory sequence.
The model essentially forgets its original training and starts drifting into default, highly generalized behaviors.
I know exactly what a lot of people listening are thinking right now, though.
What's that?
Why is this even still an issue? Why can't we just throw more compute and money at this problem?
Oh, the bigger context window argument.
Yeah. The latest models from OpenAI and Google have massive context windows now. Millions and millions of tokens. Doesn't just buying a bigger context window completely solve context rot?
That is perhaps the most dangerous and expensive misconception in the AI industry right now. Capacity is not the same thing as attention.
Say that again, because that is the crux of the issue.
Capacity is not attention. Just because a model can physically hold 2 million tokens in its context window doesn't mean it can effectively weigh the importance of a critical instruction buried on page 1 against a shiny, irrelevant piece of data it just retrieved a second ago on page 500.
Wow.
Massive context windows do not prevent rot. They actually give you more rope to hang yourself with.
Because it just accumulates more noise.
Yes. They allow the rot and the drift to compound for much longer, silently degrading the workflow before the system finally produces an error loud enough for a human to notice.
Okay, so if we can't buy our way out of context rot with bigger token windows, what are the architectural solutions? The literature outlines 3 major strategies for keeping an agent's memory clean.
Let's hear them.
The first, and most prominent, is utilizing subagents. Instead of having one monolithic, massive agent try to execute a sprawling 50-step process, you break the architecture down. You distribute the work to smaller, highly specialized agents.
If we connect this to the bigger picture, it is exactly how a corporate hierarchy functions. You don't have the CEO doing the quarterly tax accounting running the social media campaigns, and managing the server infrastructure.
That would be a disaster.
You have an orchestrator agent, the CEO, that analyzes the broader goal, breaks it down into tasks, and hands a highly specific subtask to an accounting sub-agent.
And the beauty of the sub-agent is that it boots up with zero conversational baggage.
Exactly. The orchestrator only sends the sub-agent the exact data it needs for that one task.
So it's a clean slate?
The sub-agent boots up with a pristine, empty context window, executes its specific function flawlessly because there is no noise, returns the structured result to the orchestrator, and then completely spins down and clears its memory.
The second solution to prevent rot is just-in-time context. I see developers make this mistake constantly.
Oh, yeah.
In an effort to be helpful, they try to front-load the entire company handbook, the complete API documentation library, and 3 years of customer history into the initial system prompt, just in case the agent needs it.
Which instantly saturates the context window with noise before the agent has even taken its first action.
Right. Do not do that. The solution is to reference where the information lives and give the agent the specific retrieval tools to fetch it only when it is needed for a specific decision.
And the third strategy is strategic compaction. We see this implemented brilliantly in tools like Claude Code.
How does that work?
They use a command, typically triggered by /compact, which pauses the workflow mid-session. It takes the sprawling, messy history of the execution so far and passes it to a separate model to compress it into a highly concise, information-dense summary.
It's like hitting a memory reset button.
Exactly. It preserves the core facts, the decisions made, and the current state of the workflow, but it strips out all the raw JSON payloads, the minor API errors that were already resolved, and the distracting conversational filler.
That's brilliant.
It clears the noise, allowing the agent to regain focus on its primary directives without losing its place in the larger task.
Since we know that agents will inevitably drift, hallucinate, and rot over long sessions, we have to build in mechanisms to dynamically catch those errors before they impact the business.
We can't just hope they don't fail.
No, we can't. Which leads us to what is arguably the holy grail of agentic workflows: self-correction, the yes-man trap, and steering.
A true self-correcting loop is the defining characteristic of a highly reliable, autonomous system. Future AGI outlines that this loop requires 3 distinct mandatory phases: generate, critique, and revise.
And we need to be very clear here. This is not an after-the-fact evaluation. This isn't a dashboard you check on Friday to see how many mistakes the agent made on Thursday.
No, this happens in real time, mid-execution.
It pauses the work.
The system actively holds back the final output or the state-changing action until it has verified its own work. The agent generates a draft output, critiques that draft against its specific guardrails, and if it fails the critique, it revises the output.
And it just loops.
This loop continues until the critique passes, and only then does the user see the result or the API get triggered.
But the feedback requirement during the critique phase is incredibly strict. A simple binary pass-fail is completely useless to a language model.
Because a language model doesn't understand implicit failure.
Right.
If the critique phase just returns the word fail, the generating agent doesn't know what part of its complex output was wrong. Was the tone off? Was the math wrong? Did it use the wrong tool?
It has no idea.
Lacking that context, the agent will just hallucinate a completely different, equally random response, hoping it passes.
The critique must explicitly explain why it failed. It needs to provide semantic feedback.
Give us an example.
It needs to say something like, fail. Your summary claims the project is over budget, but the retrieved financial data shows a surplus of $5,000. Recalculate and revise.
That's perfect. However, this brings us to a severe, fundamental vulnerability in self-correcting systems. The research team at Weights and Biases identifies this as the yes-man problem.
I love this concept. Explain what happens when a model tries to check itself.
Well, the instinct for many developers is to save costs by using the exact same model instance to both generate the content and then act as the judge, critiquing that content.
Makes sense on paper.
But these models have inherent biases, specific latent space topologies, and statistical blind spots.
Right.
If a model hallucinates a piece of logic during generation because of a flaw in its training, and you ask that same model to evaluate the logic, it will almost always enthusiastically approve its own hallucination.
Here's where it gets really interesting. Having the same model check its own work is exactly like asking a counterfeiter to authenticate their own fake $100 bills.
Exactly.
Of course, they think it looks flawless. They use the exact same biases, the same techniques, and the same blind spots to create the fake that they are now using to inspect it.
It creates what we call a correlated failure.
Mm.
To a developer looking at the logs, the agreement between the generator and the judge looks like a successful, robust validation.
But in reality,
In reality, both instances of the model simply fell into the exact same logical trap. The system confidently reports a 100% success rate while delivering completely flawed output to the user.
so if you want to defeat the counterfeiter, you can't ask them to check their work. You need an independent auditor. And that is what the industry has dubbed the agent buddy system.
Using an advanced framework like the Strands SDK, you design an architecture where an independent secondary model is deployed to inspect, score, and edit the worker agent's outputs.
So it's a totally different model.
Ideally, yes. This buddy model is from a completely different model family. If your worker agent is powered by an OpenAI model, you might use an Anthropic model as the buddy.
To ensure their statistical blind spots do not perfectly overlap.
Exactly. The buddy acts as a steering mechanism. It intercepts the worker's output before it hits the real world, evaluates it, and can issue one of three distinct commands.
What's the first one?
The first is proceed, which means the output perfectly aligns with the guardrails and is good to go.
Easy enough.
The second is guide, which rejects the output, intercepts the action, and provides the worker with that explicit semantic feedback for a retry.
And the third?
And the third is interrupt, which halts the entire while loop and escalates the issue to a human operator because the system recognizes it is out of its depth.
But you have to be extremely careful with that guide command. An autonomous loop combined with a highly critical buddy can quickly spiral.
Oh, for sure.
The worker tries an approach, the buddy rejects it. The worker hallucinates a weird alternative, the buddy rejects it.
It just ping-pongs forever.
Right. If you aren't careful, the agent gets stuck in an infinite loop of trying and failing, burning thousands of tokens and draining your API budget in seconds.
You absolutely must set a hard retry cap. You give the worker 3 to 5 attempts to satisfy the buddy.
And if it fails on the fifth try,
The system automatically triggers an interrupt and asks a human for help.
that is a mandatory safety measure. But I would add that while the buddy system is incredibly powerful for catching downstream errors, it is highly expensive.
Very expensive. You are literally doubling your inference costs because you are running 2 heavy models for every single interaction.
Yeah.
But a developer named Kuro on the dev community forums offered a fascinating, more efficient alternative: perception-first constraint loading.
That makes me wonder about how we can prevent the error rather than just catching it. How does perception-first loading work?
Instead of just relying on a downstream buddy to catch the drift after it happens, you proactively re-inject your core constraints at every major decision point.
Oh, wow.
Before the worker agent is allowed to make an API call, you force it to read a tiny, highly compressed constraint file. You reset its perception of the rules immediately before it takes action.
That's really smart.
It stops the drift before it manifests, allowing you to treat the expensive buddy system purely as a last line of defense, rather than the primary steering mechanism.
Stop the car before it veers off the road rather than relying on the guardrail to bounce it back. Okay, so we have designed the perfect outcome-oriented prompt. We have carefully managed our tools and explicitly defined the negative space. We avoided the JSON-constrained decoding trap by putting reasoning first.
Check, check, check.
We prevented context rot with subagents and compaction, and we deployed an independent buddy to catch the inevitable hallucinations.
It was a massive amount of engineering infrastructure.
It is. So, now for the final boss. You have built this incredibly complex autonomous system. How do you actually prove to your CIO or your stakeholders that this agent is ready to be deployed into the real enterprise environment?
Because you can't just say, well, it worked on my laptop when I asked it a question.
Right. This brings us to the ultimate test: evaluation beyond benchmarks. The hard truth that the industry is currently waking up to is that public benchmarks, things like MMLU or SWE bench, which models use to brag about their intelligence, fail completely at predicting whether an agent will actually succeed in a production environment.
Why is that, though? Every time a new model drops, the entire timeline is flooded with charts showing how it scored 98% on some benchmark. Why doesn't that translate to my customer service agent working
Because benchmarks test models on single-turn, highly bounded tasks in sterile, cleanroom conditions.
Oh, so it's not realistic.
Not at all. The data is perfect, the questions are clear, there is always a correct multiple-choice answer, but real enterprise production environments are absolute chaos.
Reality is messy.
Exactly. Production involves highly ambiguous user inputs with typos. It involves sudden API timeouts when your internal server goes down. It involves messy, unstructured data schemas, rate limits, and network latency.
So a benchmark score doesn't really matter.
Right. A model that scores a perfect 100% on a static benchmark might completely fall apart and crash when a real user changes their mind halfway through a complex multi-step conversation.
The search company, Algolia, published a piece highlighting a shocking statistic from Gartner regarding this. They found that 60% of AI production failures have absolutely nothing to do with the intelligence or the limitations of the underlying foundational model.
60%.
Yes. They fail because of bad data quality, context mismanagement, or governance failures.
Wow.
It's not the brain of the AI that fails, it's the plumbing connecting the AI to the business.
Which means if benchmarks are useless for predicting production success, we need an entirely new framework for evaluating agents. Algolia breaks this down into the 5 dimensions of evaluation.
Every robust enterprise team needs to be measuring these actively.
Let's walk through these because this is the blueprint for deployment. Dimension 1 is intelligence and accuracy. But this isn't just asking, did it get the right final answer?
No, it's evaluating the quality of the model's reasoning. Did it use the most efficient logic? Did it deduce the right context from ambiguous phrasing?
Exactly. Dimension 2 is performance and efficiency. This is your harsh reality check. This is latency and cost per task.
If your beautifully engineered self-correcting loop with a buddy system costs $6 and takes 45 seconds to resolve a basic query, it might be highly accurate, but it is completely economically unviable for production.
Dimension 3 is reliability. This is where engineering teams have to get aggressive. You don't just test the happy path, you actively try to break the agent.
Like red teaming it.
Yeah. You run fault injection tests, you simulate API failures, you purposely provide the agent with noisy, corrupted data, and you watch what it does.
Does it recover gracefully and ask the user for clarification, or does it panic and get stuck in an infinite loop?
Right. Dimension 4 is safety and governance. This is paramount for the enterprise. Does the agent strictly adhere to corporate policies? Is it resistant to prompt injection attacks from malicious users trying to break out of the system?
And does it rigorously respect data access boundaries, ensuring it never leaks user A's data to user B?
And finally, Dimension 5 is user experience. We often get so caught up in the back-end infrastructure that we forget the agent has to actually interact with a human.
Is the agent actually helpful? Is the tone appropriate for the brand? Does it ask clarifying questions without being annoying or overly verbose?
But here is the critical insight for measuring these 5 dimensions. You cannot just look at the final output the agent generates.
You have to evaluate the agent's trajectory.
This gets into the difference between trace-level analysis and session-level analysis.
Exactly. Let's say your agent returns the perfectly correct final answer to a user. If you are only doing session-level analysis, looking at the final state, that looks like a massive success. Check the box. The agent works.
But if you open up the logs,
If you open the logs and look at the trace-level analysis, the exact step-by-step path the agent took to arrive at that answer, you might uncover a total disaster.
you might see that the agent completely misunderstood the initial prompt, selected the wrong API tool, received a massive error code, hallucinated a bizarre recovery path, accidentally stumbled upon a different database that happened to contain the right data, and then confidently presented the right answer to the user.
And if it gets the right answer through a chaotic, hallucinated trajectory, that is not a success.
Not at all.
That is a catastrophic failure waiting to happen. It is purely luck, and the next time that agent runs in production, its luck will run out, and it will corrupt a database.
I want everyone listening to think deeply about this in the context of their own AI pilots. Are you just looking at the final text the agent spits out, or are you actually checking the math? Are you evaluating the trajectory it took to get there?
Which is why the ultimate mature evaluation loop pairs rigorous offline testing with continuous online monitoring.
You need both.
You need offline testing using golden datasets, curated collections of extremely hard edge cases to validate the baseline behavior of the agent before it ever sees a real user.
But offline testing isn't enough because you can't predict the chaos of humans.
Precisely. You must pair the offline suite with online monitoring, where you are continuously sampling live traces from real production traffic.
To catch the weird stuff.
You have to monitor the system to find the unpredictable, chaotic things that real users attempt to do. And here is the flywheel. Every single time you find a production failure in the live traces, you must extract that trajectory, encode it, and add it as a brand new automated test in your offline suite.
So the system is constantly learning from its own failures. It's a continuous flywheel of improvement. You are literally teaching the enterprise architecture to be more robust every single day.
It's the only way to scale.
This has been an absolutely incredible, deep breakdown of the mechanics of agentic AI.
We covered massive ground today. We fundamentally redefined the architecture, from predictable chatbots to autonomous agents.
We explored how to find the precise prompting altitude to avoid brittle flowcharts while maintaining safety.
We navigated the immense dangers of tool overload and how constrained decoding for JSON can literally lobotomize a model's reasoning capabilities.
We looked at how to fight off context rot and prompt drift using subagents and compaction, how to deploy an independent buddy system to catch correlated failures, and finally, how to evaluate trajectories rather than just final answers.
It is a profound engineering discipline.
Mhm.
Building agents is far, far beyond simply typing words into a prompt box.
It is software engineering for a non-deterministic world. And that leaves me with a final, slightly provocative thought to leave you all with as we wrap up.
Let's hear it.
As these systems rapidly mature, as agents get better at orchestrating their own subagents, as they get better at managing their own structured memory and compaction routines, and as they perfect these autonomous self-correction buddy systems, are we rapidly approaching a future where human engineers no longer write prompts at all?
Wow.
Will our jobs simply shift to writing high-level constitutions, defining the core corporate values, the ultimate business goals, and the unshakable safety boundaries, leaving the AI agents to negotiate, prompt, code, and correct each other in abstract languages and data structures that we don't even oversee? That is a wild paradigm shift to chew on as you build your next workflow.
It really is. Before we close out, if you gained value from our deep dive today, I want to ask you to do 3 quick things. Please like the episode, leave a comment, sharing your thoughts on where you think this autonomous future is heading, and subscribe for future episodes. Your support is what allows us to keep bringing you these deep technical breakdowns. Until next time, keep digging deeper, keep asking why, and stay genius.